to present you the job that we have done in the Sensibat project. So as you may know and may heard before, we are 12 partners, and we are developing sensors to be integrated inside the cell itself. So it should be in contact with the electrolyte and the electrodes of the cells. And we have partners around all Europe. So Ikerlan is the coordinator and the main developer of the BMS master. Then for the one of the sensors and the BMS slave, we have Fraunhofer. To develop the cells, we have Barta and an EIT. For the level 2 sensor, which is the third electrode, it's a Polytechnic Auditorium and bidimensional. Then Flanders Make is developing the final product of the project, which is the module, and it's also developing the algorithms together with Ikerlan and ABE based on the data that we are receiving from the sensors. And TU is also helping Flanders Make on that. And then we are using NXP chips to obtain this information from the cells, and we integrated, as I said before, in the Fraunhofer BMS slave and Ikerlan BMS master. Then we have Uni Research to help in all the administrative part of the project, and also with the part of the dissemination activities together with myself and Silvia from Polytechnico di Torino. Okay, so what are these sensors that we are developing? We have, as I said before, two different sensors. One is temperature and pressure evolution sensor. So as you can see here, we have these temperature and pressure sensors through the one side of the cell. So we can measure in different points with 2-dimension resolution. So we have a spatial resolution of the temperature and pressure inside the cell. Then we have also a third electrode, an auxiliary electrode to measure the voltage of different parts of the cells, and we are also doing impedance measurements of different parts separately. Okay, so this is the work plan of the project. We started from scratch, developing the cells and developing the sensors. We are not using any commercial cell or sensor. Then we introduced the developed sensors in the cells, and we try to validate that the cells are working as the cells without any sensors. And the only thing that we have is that what we want is to have more information about what is happening inside the cell. Then we have developed a module consisting of 6 cells with L1 sensor, so with pressure and temperature measurements inside the cell, with 5 ampere-hour both cells. And we developed also state algorithms based on this new data, and everything is implemented in the BMS master. And we also did the cost-benefit analysis, and right now we are finalizing with the recycling study. So you can see here from this work plan what we have achieved and what we should finalize in this last month of the project. So as in every project, we define the specification and requirements. We develop the baseline cells without any sensor. Then we develop the first small L1 sensor for 1 ampere-hour cells. Then we jump to 5 ampere-hour cells, and we also did a proof of concept with L2 cells. So the work plan is different for L1 and for L2 cells. For L1, we developed from sensors, cells, then module, and then we put also the BMS master and all the algorithms and everything. But with L2 cells, we finish our work with the proof of concept at cell level. Okay, then we have developed also the readout circuit for this sensor matrix. We did the cost-benefit assessment. We did the testing and validation, and at cell level, we are right now doing or trying to do it at module level. We are having some problems there with the readouts and with the cells itself also. We have developed the BMS slave and the BMS master, and we have developed also the algorithm. So right now, where we are is we are developing, or we are doing the validation and the testing at module level, and we are finalizing the recycling study. Okay, so I am going to explain the level 1 sensor more in detail. So this is the level 1 sensor for 1 ampere-hour cells. So we measure the temperature by resistive elements. So it's a nickel aluminum alloy, which, as you can see here, is quite linear from -20 degrees to 100 degrees Celsius. This is quite good to have sufficient resolution, and it's quite repetitive. So we are quite confident that the measurements that we are obtaining from these resistive elements are good for us and are usable in the range that a battery can operate from, for example, from 0 to 60 degrees or so. And then for pressure, we are using capacitive detection elements. So we have capacitives here. So if we apply a certain frequency, we can measure the capacitance of this element, and as it changes, we can obtain the pressure that we apply from the outside to the cell, or the cell is applying to the outside. And in this case, for 1 ampere-hour cells, we have 12 measurement points, and you can see here how we implemented in the cell. So it's between the electrode and the pouch bag. And what we realized when we introduce it into the cells is that we have a problem with the stability of the sensor in contact with electrolyte. So the encapsulation of the sensor, this is not exactly a sensor, it's a sensor dummy where we use the same procedure to develop it, and like that we can at a small scale demonstrate or not if it is working. And as you can see here, the sensor encapsulation breaks down when it is in contact with electrolyte, and we added an tempering step that is based on having the sensor at 200 degrees Celsius for several hours, and after that we put it again inside the electrolyte, and there was no delamination of the sensor. So we validate that like this it can be usable inside the cells. This high temperature process did not affect the temperature resistors, but it affected the capacitive material of the pressure sensors. So we needed to start again from the beginning and change these capacitive elements, because the ones that were selected at the beginning, they cannot stay at these high temperatures. Okay, after that, we started the first validation phase with 1 ampere-hour cells. So we cycled the cell at 25 degrees for 200 cycles. And as you can see here, in red, we have the cell without any sensor, and in blue, the cell with sensor. So we have two cells, two baseline cells and two cells with sensors. And the evolution of the cell is quite similar with and without sensor. And after that, we also opened the cell, and we saw that it is in good condition. The sensor is in good condition. So it seems that the electrolyte did not affect the sensor element. Okay, after this, we jumped to 5 ampere hours cells, so bigger cells, more sensor elements. So we jumped from 12 to 35 sensing points. And another thing we needed to change is the carry-through of the sensor, the positioning of it. At the beginning, it was between the two positive and negative electrodes of the cells, but then we needed to place it in one side because it was too wide to put it on top. Okay, we also try to do some kind of integration at a small or just at in a pilot line, and we demonstrate that it was possible to put the sensor in the cell stack using an automatic positioning unit. So we demonstrate that the industriality of this sensor, once that it's built, so to put it on the cell, it is quite easy. Okay. We needed also to adapt a little bit the sealing process of the cell, because we put here like a glue to seal the cell perfectly and not to have leakage of electrolyte from the inside to the outside. And this is something different, the one that we are using on the tops of the cell. Okay. We started this validation with 5 ampere hour cells. So we tested 3 cells with a cycling protocol and 2 cells at calendar aging protocol. 2 of the cells that are cycling, we test them with a pressure setup. So they are under pressure, but not only under pressure, we are also measuring the pressure that the cell puts on to the outside. So like that, we tried to validate the information that we are obtaining from the sensor. So we have like a double check. We are obtaining the information from the sensor, and we are also obtaining from the outside of the cell. And the same for the temperature. In both cases, from the outside, we were only able to measure it in 1 point instead of the 35 points that we are able to measure inside the cell. Here you can see a comparative study comparing the baseline cells, which are the dotted ones, and the L1 cells, and the ones that are under pressure, because the baseline cells were 2 cells both under pressure. They behave quite similar in capacity evolution and also in internal resistance increase. And as expected, the one without any pressure applied from the outside, it dies before the other cells. So we reach around 800 cycles, but take into account that this is in a very aggressive environment at 45 degrees Celsius, 100% DOD 0.5 C. So here we can demonstrate that in this environment, in this aggressive environment, there is no difference in life or in cycle aging between the cell with and without a sensor. But we had some problems with those sensors. As you can see in those two pictures here, the traces of the sensor, so in the free-through area, were eaten and they were completely erased in some parts. So at the beginning, we were able to measure the pressure and the temperature from the sensor, but at a certain point, the electrolyte gets inside the sensor and it is corrosive. It started to erase the wires or the wires of the sensor. We didn't have any leakage to the outside of the cell, or not any. We had a little bit, but it was through the sensor, not through the heat, through the closing area that we have here. And another thing that we saw is that there is a solid expansion area at the sensor free-through. So here the cell is wider than in the other side. So where it is placed the sensor, it's wider. And this is like a pressure paper or something. I cannot remember the name of it, but it's a pressure sensitive paper. So it is darker in the places where it is more pressure. So here again, we can see how it's the same as in here. We can see how in the surroundings of the sensor free-through, we have more pressure than in the other parts of the cell. We did a postmortem analysis, and we saw that there is no failure of the sensor itself. So the problem was just here in the area where it is placed the sensor free-through. So it seems that the glue that we put here to seal the cell has an impact on the sensor, and with time it deteriorates and the electrolyte gets inside the sensor. Another thing that we saw is that, as we saw in the previous picture, the cell stack shows much bigger stack height at the edge where the sensor free-through was placed. So here we can see that it's like widen, and we started to also to analyze the electrodes of the cell, and we saw that the anodes were in not good condition. We can see some copper at the active area, especially at the edges where the sensor free-through was placed. So here, and there is also a thicker cell stack that linked to the anode, that, as we can see in the next picture, there was almost no impact on the cathode. So all these all this problem was due to the anode. Okay, we detected this during this summer. So we didn't have too much time to solve it. So what we did, we used the same sensor, the same glue, everything the same, but we used we placed instead of in contact with electrolyte, we placed on top of a baseline cell, which is a normal 5 ampere hour pod cell. Then we placed the sensor, and we did like an additional pod layer to the outside to have the sensor inside the cell with the vacuum and everything as it was placed on the inside. This was something that was beforehand detected as a risk of the project. So in this case, we didn't have too much time to develop the cells from scratch, to start doing all the validation, and then to have the modules on, in order to be sure that we won't have this kind of leakage problems at module level, and in order to be able to validate that in the case that we are able to develop sensors that can be in contact with electrolyte without any problem, we are able to have new algorithms, and we are able to work with the module with these new metrics. We developed these new cells. So you can see here how we develop the cell without any sensor. Then we put the sensor on top of it, and then we close it again. Of course, as we have 2 postbacks, the cell is a little bit bigger, so we changed a little bit the design of the module, but we had some time to do it, and the people from Flanders worked really hard to have finalized I think that by the beginning of October. Okay, so what we have in the module, we have a sensor readout circuit. So this is the sensor, and we have a PCB board to read all the information from the inside for each cell. So we have one PCB board for each cell. Then we have the BMS slave to control these PCB boards and to transfer data to the BMS master, which is this one. And in the BMS master is based on a rapid prototyping platform to quickly adapt the information that we have on it. For example, the algorithms, and to be able to validate in a really fast way the last versions of the algorithms that we are developing. And this is the case where we are now. We are validating everything, and at the same time we are developing the algorithms. So we are working almost in parallel. And this is the module. So we have 6 cells. So the cells are between cooling plates, that are those blue parts of the cell. Then we have them to have an easier connection of the serial connection of the cells. We have the cells one to one side, so to the left, and the next one to the right. So we have 3 sensors to with a free through area to one side, and the other ones to the other side. Then we have one thermocouple to validate the measurements that we are obtaining from the inside. We have one thermocouple for each cell, and we have 3 pressure sensitive elements on one side of the module to measure the complete pressure that is doing the cells to the outside. Okay, so this is the complete design with the pipes to have the cooling liquid inside, and outside the cell, we can reverse the flow, so it's not inside, outside, can be in the other way around. With this, we want to also be able to produce different temperature gradients in the cells, and to detect, to demonstrate that we are able to detect these different gradients with the sensor that we have placed on the cells. So this is the module itself. With it's not this was a picture of beginning of October, so it is not completely finalized, because as you can see here, there is only one readout circuit, but right now we have 3 readout circuits on one side, the other ones on the other side. Yes, the control unit, the BMS master, and everything is placed on the place that it should be. The same for the power module connection unit. So right now it's everything working, and we are validating the algorithms that we obtained in our project. So the storyboard for L1 sensors is we developed the anode material development. It's from Barta. Then we printed the temperature sensor. We also do it for the pressure sensor. We test everything. We put all together. We build the cell. We validate the cell, and then right now we are validating at module level. And about level 2 sensor, here we developed, as I said before, an auxiliary electrode. I think it's we place it on the separator of the cell, and in this case we have 2 separators. On one of them we have this auxiliary electrode, which is based on a printed LFP. Okay, so those are the cells. So we have a printed LFP reference electrodes to measure separately the potential of the in this case the NMC and the graphite, and we did also some tests to measure if something inside the cell has changed. Apparently, we can also detect a small increase in internal resistance of the cell. So this electrode somehow affected the behavior of the cell. But we also did aging tests, and we can assure that this increase of internal resistance and this third electrode did not affect the behavior, the long-term behavior of the cell. And what can we do with this kind of third electrodes? For example, we detected that we have an overbalancing of the negative electrode that we can see here at, I think it was C divided by 10 C rate. So at very small charging and discharging rate, we can see that the negative electrode does not operate on the boundaries like it does at, for example, at 1C here or here. We can also detect that at higher C rates, the negative electrode, again, in this case, in the opposite way, operates in a wider potential window. As you can see here with a 3C discharge and here at a 3C charge, it goes upper and lower the normal operation window of the anode, and is this means that we can have some metallic lithium deposition in those points. This is also something, but in a completely different way. We measure with L1 sensor. In this case, we measure an increase of pressure every time that we perform this 3C charge, and this increase of pressure is not reversible. For example, in a normal charge discharge, we have an increase of pressure while we are charging the cell and a decrease while we are discharging it. But in overall, the average pressure of the cell, it maintains a constant, but every time that we perform this 3C charge, this average jumps up, and it's at something like 50% more or so every time that we perform this 3C charge. And we not only have a big increase of pressure, a reversible pressure increase, we only have a non-reversible part. So this means that we are having some problems on the cell at this have a really high currents. Okay, and about the cost of these sensor elements, they are completely different systems. And as you can see here in this graph, this is the cost or the material cost breakdown for L2 sensor, so the third electrode, and black, so this something less than 10% is the price of the sensor materials, and the rest are the typical materials that we can find in a normal cell. And in the other side, for L1 cell, we have instead of 10% for the sensor, we have the 10% only for the materials that are in a normal cell. So the cost of the L1 sensor is much higher than the cost of the L2 sensor. And you can see here we did some projections at industrial scale, and we estimate a cost of around 100 euros per kilowatt hour for 5 ampere hour baseline cells, and 30% more for smaller cells. And as you can see here, if we add the L2 sensor, we have an increase of less than 10% of the price for 1 ampere hour cells. But in the case of L1 sensor, we have more than the double at euros kilowatt hour price. So in summary, the L1 sensor represents an increase of more than 120% of a baseline cell without any sensor. This means, for example, 0.08 euros per kilowatt hour per cycle. So it's too expensive to use it at all cells in a module or in a battery pack, in any application. And this is without considering the dedicated readout electronics, that they are also complex and they are not as simple as in the third electrode case. So we find difficult to have this kind of sensors in industrial applications. They can be usable at research or at a cell development level, but we find it difficult to implement them in a massive way in applications. On contrary, the level 2 sensor represents only an increase of the cell price by 5%. So this means that considering that a baseline cells reaches 3,000 cycles to have a cost parity for a kilowatt-hour cycle, we need to reach 150 cycles more when we are using this new sensor. And as we have more information of the cell, we think that this is something possible. And if we can increase more the cycle life of the cell using this sensor, we will lower more the total cost of ownership of this L2 1 ampere hour cells. This sensor is also very easily introducible at industrial or production level, considering the production methods that we have nowadays in the battery manufacturing industry. And on the opposite way that we said for level 1 cells that we need a real electronics and it's expensive, needs space and all these things. In this case, the cell electrode is something simple, and it does not require high or complex readout electronics. It can be implemented in quite simple BMS. The only restriction is only to have one more voltage point for per cell in the battery pack. So all the things that I saw today are part of different Sensibat deliverables already published or that will be published in the following month before the end of the project. So everything is public and you can see on our website. We will launch also on December our last newsletter. We are also doing a video that will be also made public in LinkedIn or in the different platforms that we have in the project. And I think that this was all from my side. Thank you very much. And if you have any question, I am here to answer, or maybe in the next meeting with the people from Instabat and Spartacus, maybe they have more questions.